Good afternoon. So, in the last class, whatever we looked at, I just want to re-look at it once again and tell you some of the things that I missed out. Okay. First and foremost, I hope you all got the set of exercises on Moodle. All those exercises is what I am going to be repeating here, uh, and all of them pertain to argon. Okay, and the whole idea is to simply learn some simple techniques in lamps so as to be able to reproduce some of the things that we actually know. Okay, so in exercise 2, one of the things that we did was we initialized the kinetic energy of a system, right, and then simply started evolving it in NVE. And what we found is, when we looked at the equilibrated structure, the temperature turned out to be half of what we set it to be. We set it to be 300 Kelvin, and then we started integrating it, and then it turned out to be half the structure. I just told you that this is going to happen as if the atoms are actually going to be vibrating about their mean positions, basically exploring the harmonic region of their intraatomic potential. So I want to show a simple mathematical means of seeing actually how that actually works. In doing so, we will actually be introducing some few results from statistical mechanics also. You don't need to know the proof of all of these things, but if you just follow my reasoning, that will be more than enough. So for example, so we have to talk about something called as the equipartition theorem, which essentially tells you how the energy is essentially distributed amongst the various degrees of freedom that's available in the system. Okay, so the first equation that you see on the slide, which says that the average of xi dou h by dou xj is equal to del ij kbt. What does that mean? It means that the ensemble average of this quantity is equal to del ij kbt, where kb is obviously the Boltzmann's constant and T is the temperature. Xi and xj are actually either the position degrees of freedom or the momentum degrees of freedom. So equation 10 can be written either as equation 11 or equation 12. So Qi times dou h by dou Qj del Ij kBt, Pi dou h by dou Pj del Ij kBt. This is a result from statistical mechanics. You can actually show, and these bracket essentially means the phase average or the ensemble average. Okay, so if you want to quickly see what that means, I will just write it down, but not necessarily the entire proof. What I meant was, if you want to calculate the average of some quantity, say x, this means integral over the phase space x integral of the entire phase space That's what it means. It's written a little bit badly, but you're able to follow what I mean by that. So if you wanted to calculate the average of the energy, so you just have to find out what the energy is, what is the probability that that particular energy is occurring, right? So that exp minus beta h is essentially the telling you the probability. So that particular quantity multiplied by e to the power minus beta h integrated over the entire phase space divided by integrated over the entire phase space e to the power minus beta h is essentially going to give you the average value of that quantity. So when I am talking about the average of this quantity, it means this quantity is going to replace the x in the PowerPoint slide that I just wrote down now. Okay, so when you do that, it so happens that it is just del ij kbt. That means if qi and qj are the same, only you have kbt. This can be proved rigorously in statistical mechanics. So now let us take a look at equation 12 and expand it a bit. Okay, now dou H by dou Pj. H is basically, what is H? Alright, dou H by dou Pj is what? Q dot, right? So if you rewrite it, you get Pi times the average of Pi times Qj dot is equal to, which can be written as Pi times Pj divided by m. Momentum divided by the mass is nothing but Qj, just the time derivative of the position, right? And that happens to be equal to del Ij times kBt. And therefore, if we are talking about exactly the same degree of freedom of the system, it's equal to Pi square divided by 2m. The average of that quantity is actually equal to half times kBt. So what this is saying is, what is Pi square by 2m? What does it look like? It looks like the kinetic energy that is associated with, say, Px of atom 1 or Px of atom, Py of atom 1. It could be anything, right? It depends on the each degree of freedom. We are talking about one particular degree of freedom, right? So the average kinetic energy that is associated with each degree of freedom turns out to be half kBt. So if you are going to consider all the degrees of freedom that is existing for the entire system, then you can sum over the 3n degrees of freedom that's available to the system, and you happen to get summation over I equal to 1 to 3n, the average of Pi square by 2m is equal to 3n by 2 kBt, which is nothing but the average kinetic energy of the entire system that is associated with the vibration of the atoms, right? So this of course has come from the equipartition theorem, which we are not proving right now, which I am expecting you to accept as it is, okay? But if you accept that, that is actually a general, that's actually a general thing. There is no assumptions that's gone in there, and so even this one is quite general. There is no assumptions that we made. As long as it is a classical system, we are talking about the kinetic energy of the system. This term is here is clearly the average kinetic energy associated with the system, right? And that is related to the temperature, right? So the average kinetic energy of each degree of freedom at equilibrium turns out to be half kBt, and therefore if you take a look at this expression and reorganize it a bit, you get the expression for temperature, which is 2 by 3 the total kinetic or the average kinetic energy of the entire system divided by n times kb, right? So in this expression is quite general. You might have seen it for ideal gases, but in the derivation that we just made, we didn't make any assumption concerning the nature of the system. Therefore the expression for temperature for any system is always 2 by 3 the average kinetic energy of the system divided by n times kb. So when molecular dynamics is actually calculating the temperature of the system and printing it out in the log file, it is actually using this expression, okay? Now if you take a look at the other expression, right, Qi times dou H by dou Qj del Ij kBt, then the only part of the Hamiltonian which explicitly depends on the coordinates is actually the potential energy, right? The kinetic energy depends on the momentum. The potential energy only depends on the Q's, right? So we can write the previous expression as Qi times dou V by dou Qj is equal to del Ij kBt. Now if you consider the what is dou V by dou Qj, what does it look like? The rate of the derivative of the potential with respect to position, what should it force, right? So if you consider the alphath atom and write down this expression, dou V by dou Qj must actually be the negative of the force by definition. So you have here Qi alpha, Fj alpha, the average of that quantity is equal to del Ij kBt. For I equal to j, you have Qi alpha, Fi alpha, the average of that quantity is equal to 3 times kBt, okay? So this quantity here, and if you average it over the entire if you sum it up over all the atoms of the system contained in the system, then you get expression 21, where you have, when you sum it on both the sides, you get basically 3n kBt. So this expression that you see right here is called as the virial of the system and is represented by this F right here, okay? So clearly you have the average of this quantity F to be equal to minus 2 times the vibrational kinetic energy of the system. Okay, so this is something to keep in mind. These are two consequences of the equipartition theorem, or of these two expressions, right? Now let us see what happens when we actually set the temperature of the system to T0 without actually displacing the atoms from their initial equilibrium positions. When we do that, the entire energy that has been dumped into the system is purely kinetic, right? So the total energy of the system is 3 by 2 NkB T0 at the instant that we set it, right, in exercise 2. Is that okay? Are you able to accept that? Now this energy has to be maintained throughout the simulation. That means the kinetic energy that is being given to it must be somewhat portioned properly between the potential energy components and the kinetic energy components as the system evolves. Okay. So as time progresses, this energy has to be divided between the potential energy and the kinetic energy component, and at equilibrium, once the system has reached equilibrium, the average kinetic energy is known. It's going to be 3 by 2 NkB T equal, which is going to be different from this temperature we set it to be initially, correct? So now what is the average potential energy of the system? So the average potential energy of the system is rather difficult to calculate under very general, for us, if you assume general cases like Lennard-Jones, or if any other kind of potential, it is difficult for us to calculate. Just for the purposes of illustration, I have taken a potential which is basically a set of non-interacting particles where you have the atoms initially at their original equilibrium positions, and any displacement from their initial positions gives it energy through the spring constant K. Okay, so the average energy of this potential energy of the system at any instant of time is given by this expression 25, where K is basically the spring constant, Q is the position of the particle at any instant of time, and capital Q alpha is basically the initial position or the reference position from where it is actually moving to gain that energy. Okay, so if you calculate so now if you take a look at it, K times Q minus Q alpha is nothing but the force, or negative of the force, spring force. So we have replaced that term with F alpha minus F alpha dot Q alpha minus capital Q alpha, and we want to take the average of that quantity. And if you look at this expression carefully, this is basically a constant. This Q alpha is basically a constant, which is telling you which is basically the reference position of that atom, and this becomes minus half times average of this dot product plus half times the average of this dot product, because the average over Q alpha doesn't give anything because it's a constant. Now since the atoms are actually vibrating about their mean positions at equilibrium, this average force on every atom becomes 0. Okay, therefore this quantity essentially vanishes, and this is related to the virial that we just saw, right? If it was very similar to that, right? It is half the virial value of the virial, right? So the average potential energy of the system is negative half summation over all the atoms F dot Q, and since F dot Q is nothing but the virial, it is nothing but 3n kBt, or this entire thing becomes 3n by 2 kBt, right? So that's what I'm trying to say here in equation 27. So the total energy of the system is nothing but the average energy at equilibrium is nothing but the average potential energy plus average kinetic energy, and that has to be always conserved and is therefore equal to 3n kBt times the 3n kBt equilibrium, correct? Since the energy is conserved. So we just added up these two. This is nothing but 3n by 2 kBt. This is also 3n by 2 kBt, and I'm just adding them up, and you get 3n kBt equal. Since energy is conserved, 3n kBt equilibrium must be equal to the dumped in energy 3n by 2 kBt naught, which is the initial temperature that we set, right? So when you look at this expression carefully, you will see that the equilibrium temperature becomes equal to half the temperature at which we set. So this is a very simple way of showing explicitly that this equilibrium temperature that the system reaches is actually the half the set temperature. Now you have to remember that this exact relation, yes, potential, yes. This exact result is valid only for potentials which are like quadratic in Qi and Pi, okay, or if you look at the Lennard-Jones potential, there is a small region here where it's harmonic. So anywhere if the atoms are just vibrating about that position, okay, if the deviation from that position is not too much, even then your equilibrium temperature will settle down to T set by 2 approximately, okay. So this is some justification as to why that is happening. So now I want to take a look at the next exercise. I think in the next exercise, what I wanted to do was, I wanted to show you what happens when you simply use this fix called fix NPT and try our best to relax the system to a certain pressure and temperature, okay. So what I have done first is, initially you create velocity of about 300 Kelvin, okay, distributed in a Gaussian manner, and then perform a NVE, okay, and now at the end of this run, the temperatures are not going to be around 300 Kelvin at all, they are going to be in fact somewhere around 150 Kelvin, and then I just set fix to all NPT. If it is temperature, you ramp it up from approximately 150 Kelvin to 300 Kelvin with a T damp parameter of about 0.1, and then if it is going to be, if it's the pressure, for the pressure you have different options that's available in lamps. ISO means do it isotropically for all the phases, like I mentioned last class. From the current pressure that it is in, it was approximately 70,000 bars, to about 1, which is what we want, and there is a corresponding P damp parameter. So this one and this one are the values, are corresponding T damp and P damp values, and there is a convention specified in the manual that, not a convention, that the default values or the values that you should use depends upon the time step. So for T damp it is approximately about 100 times time step, and P damp is approximately 1000 times the time step. In most of the cases that I have used, that I have worked with, these settings are sufficient. Very rarely will you actually have to change this, okay. Now the whole thing is, after performing this NPT fix for about 10,000 steps, so we have already done something for about 3000 steps right here, right, and then I am performing something for about 10,000 steps. So totally the simulation has run for about 3 plus 10, 13 picoseconds, right. After that, what I am trying to do is, I am trying to isolate the system from the surroundings and just do a NVE and check if the temperature and the pressure that I have requested have actually reached the values that I wanted it, okay. This fix is supposed to dump in energy, and it is also supposed to change the dimensions of the box so as to reach the required pressure and temperature, okay. So now, so this is the energy. So I mean, I didn't describe what exactly these partitions mean here last class, that's why I am showing it again. So you can see that the first 3 picoseconds, the total energy is a constant, This is the energy variation over the entire simulation. Okay, the first 3 our simulation was divided into 3 parts: 3 picoseconds of NVE, 10 picoseconds of NPT, and then again 5 picoseconds of NVE. Right. So the first 3 picoseconds illustrates the region where the NVE was carried out. So total energy is remaining a constant, and the kinetic energy and the potential energies are also shown here. Then we have the NPT simulation where several things are happening. So the kinetic energy is slowly increasing because we are ramping up the temperature, right? Then the potential energy is decreasing and total energy is decreasing. And then again I stopped all the NPT fixes and continued my NVE fix for another 5 picoseconds, and once again I see a constant energy and mildly fluctuating potential and kinetic energies, right? So the whole point is whether this thing has actually reached equilibrium. So the pressure, it started at 70,000 atmospheres and it's somewhere here. So this is not still 1 atmosphere, this is still in the order of about 1000 atmospheres, right? Because the scale is like going at 10, 20, 30, 40, and I have printed it in thousands of atmospheres. So although this appears to be small, this is not the pressure we want. So you can take a look at the log file. So this is what I printed out, just the information. You see so the last column and is volume, and the column before that is actually pressure. So this is the volume and this is the pressure, still about 1540 bars, still not reached the required pressure that we want. The temperature also, this region is NVE, so it was oscillating about 150, right, or from 300, and then it starts oscillating about 150, about 3 picoseconds. I stopped it at about 3 picoseconds because the NVE run that we carried out previously for a longer period of time seemed to show that at 3 picoseconds it had reached some equilibrium value. So I don't have to continue that run for a longer period of time. And then from 150 to 300 I have tried to ramp, but I ramped it for about 13 picoseconds and then I stopped it and continued my NVE run. But when I continued my NVE run, the energy that was dumped into the system is still making it oscillate only at around 250 Kelvin. We still, again, when it comes to temperature also, we have not yet reached the required temperature that we require the thermostat to do, right? We want the system to be at 1 atmospheres and 300 Kelvin. Okay. But nonetheless, the pressure has still come down from 70,000 bar to about 1500 bar, and like I showed you last class, what's essentially happening during the NPT run is the expansion of this whole system. I think we saw that, right? Yes, we saw that. So now if you run it for a longer period of time, so for example, if I run this thing for say a longer period of time and look at the temperatures, it happens to be slightly better. Okay, for 20,000 or 30,000 steps, if I do this NPT, it happens to be only slightly better. It is still not, and even the pressure. Okay, for example, before coming here, I ran it for about 50 picoseconds. The temperature came to about 280 Kelvin, and the pressure was still around 600 bars. Okay, so sometimes you may have to run it for a very long time before you are actually able to achieve equilibrium, and you have to check it. How do you check for equilibrium in MD? How do you check for equilibrium, whether it has reached equilibrium or not? You stop the way I generally like to do it is stop any exchange of heat or energy with the surroundings. That means stop any NVT, NPT fixes, and then do an exclusive NVE. So if the system has reached equilibrium with the surroundings, then its temperature and pressure should be what you want. Otherwise, it will just shift and show you a different value. There is another way by monitoring what is referred to as the velocity autocorrelation function. Okay, we will come to that a little bit later, but qualitatively what that function is going to tell you is how soon has this system lost memory of its initial configuration. So remember, you have set the initial velocities and initial positions, right? And the system is supposed to behave independent of that. No matter what initial configurations that you gave or the temperature that you gave, at equilibrium it is supposed to behave independently of your initial condition. The velocity autocorrelation function is one way by which you can check whether the system has lost any memory of its initial state, and that is another method by which you can actually check if the system has reached equilibrium. But this method I like it because it's quite intuitive, simply because the definition of equilibrium is you have to isolate the system from the surroundings and see if things are changing. That's the definition of equilibrium from thermodynamics, right? And we are doing exactly that. We are stopping any NVT fix and we are performing an NVE fix, and NVE means an isolated system for a given input. Yeah.
So autocorrelation will become 0.
Yes, the autocorrelation function will become 0 as time progresses to suggest it will oscillate about 0. Okay, we'll see that if we have time. Okay.
So what do you mean by memory of its previous state?
Not previous state, it was the initial configuration.
Systems means you are referring to the memory
Of the system itself, of the bunch of atoms itself. It should not depend on, okay, so you say for example, let us consider you took a system, you initially, okay, this is a good way to probably explain that. So you initialize the velocity of the system in a particular way at 300 Kelvin using this random seed, right? If I change this random seed, it is going to get initialized in a different way, right? Yes or no?
Yes.
Right? Different sets of atoms are going to have different velocities. And now I run the simulation. No matter what I give the initial condition, the equilibrium state of the system must not depend on these configurations, right? It should not, right? Any as time progresses, it should start exploring its equilibrium state, and that will happen after some time. For example, if the 300 Kelvin becomes 150 Kelvin not instantaneously. It takes some time for it to become 150 Kelvin. If you look at that graph, it takes about, I don't know, maybe half a picosecond or something like that. So it takes some time for the vibrations to actually die out and reach 150 Kelvin, right? So now, no matter what was the initialization of the velocities at this spot, it should always start reaching equilibrium. And once it is starting exploring the space here, it is not possible for the system to tell you whether this state was initialized with a random seed of 197248 or whether it was initialized with some other random seed. It has completely lost memory of its initial conditions, right? So that should happen to any system. So
Random seed should always be 6 digit.
always be?
Should it be 6 digit number?
No, some number, some integer you can give. It doesn't have to be any 6-digit number. I just gave something that came to my mind, or I just typed something without even looking at the keyboard actually. Okay, so
If we put the same sequence each time, what we get, the initial condition will it be the same?
yes, because it's really not, the computer is not that random yet, right? Yeah, pseudo random. So yeah, so when you do it a little bit longer, when you just have NPT, or after NV you just have NPT and do it a little bit longer, it still does not converge to the pressure and temperature that we require. Okay, so this equilibration has to be done very carefully and in steps. Okay, so so next thing what I'm going to do is I'm just going to perform, after this NPT, I'm going to perform an exclusive NVT relaxation using the Nuse-Hoover thermostat. No NPT. Okay, just holding whatever volume was fixed, we will hold that. Whatever volume was created, we will hold that. What happened? Huh? Nuse-Hoover. What is it? It's a thermostat. So that is actually, it is a methodology by which the dynamics of the system is changed. Even NPT is actually a altered dynamics of the system. You have to add terms to the set of differential equations that you are solving so as to allow it to input heat or to change the volume. Okay, so Nuse-Hoover thermostat is a thermostat that's available in lamps for you to implement a thermostat, basically increase the temperature. That's it. Now there is a lot of math, there is a lot of derivation to actually understand and see why this actually explores the NVT ensemble. Okay, now this is not, I'm not going to do that, but then that would be a coding course and it would require a different type of background in order to be doing that. Okay, we will see how to use it. We will see how to use the Nuse-Hoover thermostat and what it does for our system.
Sir,
Yes.
when we write the command fix one all NV, one refers to the
Fix ID. Fix ID.
okay, it refers to the fix ID.
Fix ID, which can be referred to later on in the script. So if you say unfix one, it means stop that. You can also say fix some other name. You can say fix, I am NVE fix. You can say that. Okay, it is some name that you give so that you can refer to it later on in the script. So here everything until this part remains the same, but now what I am going to do is I am just going to say fix to all NVT temperature from 300 to 300 with a T damp of about 0.1, and I am going to run it for about 10 picoseconds. So what is there any difficulty? You are looking at him and saying this is difficult, is something complicated here, or you have?
Can you go to the NVT script? You start with 300 and end with 3.
Yeah. So
Shouldn't NVT contain two different initial and final temperatures? Shouldn't they be different?
not necessary.
The actual usage is that start from one temperature and
Yes. Yes, you can ramp it up, or you can start at 300 and end at 300 also. Both are fine. You see, our initial temperature was what? 150. We tried to reach 300 using this NPT, but it reached some 280. That was close enough to 300. So I am starting at 300 and ending at 300. Okay. Now, if there is a huge difference between the current temperature at which the system is and the temperature to which you want to go to, then it is a good idea to ramp it up slowly. Okay. Otherwise, you can actually give the starting temperature and the ending temperature to be the same value, and basically what it does is it maintains tries to maintain the temperature of 300 Kelvin. So this has been run to about 10 picoseconds.
If you have like reached like 28 280 or something, and if you give like 300 to 300, then will it try to make sure like it comes to 300?
Yes. If you 280 to 300 means it will come to 300 from, it is going to try to make it to come to 300 from 280. Yeah, but the initial temperature that it is going to try to give is 280, and then slowly as a function of time it is going to ramp it.
Even increase the number of iterations I'm running, say like 20,000 also, then the system is still the same. Because I'm still maintaining it at 300, so it will just reach 300 and stay at 300.
Yes, yes. So when I did this,
So if the temperature is not changing, then what is NVT doing exactly?
no, the system, it is trying to change the temperature. Your system is not at 300 yet. It is still at some 250 or something, no?
Okay.
See, this is just a extension of the exercise 3. Exercise 3 basically stopped here. There was an NPT run where we tried to ramp it up from 153 to 300, and we observed the results, and we saw that it was not reaching 300. It was some 200 and odd Kelvin, right? I am just adding another fix to only ramp the temperature. Yes.
So in the previous one, you've seen that the temperature reaches about 275 to 80.
Yeah.
Then why are we giving 300 to 300 and shouldn't it be 280?
You can give 280 to 300 also. It doesn't matter. It will start from 280 and slowly ramp it up to 300 in this time step. Before it reaches this time step, if it happens to reach 300, then it will maintain 300. But that's not what it is going to do. If you say start temperature and end temperature, it means it will start at 280 and over that time frame it will reach 300 Kelvin. Okay, is that clear? But if you give 300 to 300, it is just going to maintain 300. It is just going to start at 300 and maintain that 300 value for the entire time period for which this fix is held.
We can increase the number of iterations if it will anyway start from
I didn't follow you.
if NVT anyway will start from 300, so we can reduce the number of iterations. Instead of 10,000, we can put
You can try. This 10,000 is not something that was derived. You just
what
tried.
iteration will it immediately bring it to 300?
What is that?
NVT.
What?
In which step will it bring it to 300? Like, is it the first step itself? Or
The first step, it is going to put some heat into it to try to bring it to 300. Okay. But then as a function of time, that it may not, enough energy may not have been pumped in for the entire system to have got 300. So it has to continuously do it. So there might be some, see, what does temperature mean? The average temperature could be 300, but there could be higher and lower temperatures within the system. There might be heat transfer going on within the system, but that's not what you want. You want the entire temperature to be on an average oscillating about 300 Kelvin. Okay, so it will start at 300 and try to maintain it at 300. If you do 300 initial and 300 end over the entire time period. Okay. If you reduce the number of steps, you can try. It may reach. It may give you an equilibrium state of 300, or it may not reach. Also, for example, if I just did this for one step, if I did this for just one step, do you think it would be 300?
No.
It would not be 300. So there is sufficient. You have to give it sufficient time so that it reaches equilibrium with the bath that is pumping in heat to the system, right?
So we told like the very first iteration it will try to make it 300, and maybe in the second iteration it will go to some.
It might go down again. It will fluctuate.
So, but the very first iteration will reach 300.
Will reach 300. Yes. And if you said 280 to 300, the very first iteration will be 200. Yeah, it will start with 280 to 280, and it will go to 300 in that time span. So now if you see, so this is our NVE part. This is the temperature as a function of time here, right? So this is our NVE part, the first 3 picoseconds, followed by 13 picoseconds of our NPT, which ended somewhere here, and then I do a NVT to try to make it oscillate about 300, and now it's,
In the very first iteration it will reach 300, but it won't be in equilibrium.
yes,
If we are giving one as a
Yes, it won't be in equilibrium with the bath. Somewhat oscillating about 300, definitely better than the value that it ended in previously. But of course, we will know this only when we stop this fix and do a NVE run, right? Otherwise, we won't know, right? Now, of course, what should happen to the pressure? So the pressure is still not what we want, obviously. It continues to be what it was. Actually, it cannot be what it was, it will change a little bit, right? It will change a little bit because you are holding the volume fixed and you are increasing the temperature a bit. The pressure is likely to increase a bit, right? So that's what you are observing here. And there's nothing interesting to see about the energy, it looks exactly the same. Okay, this is the region where the NVT has been run. Okay, in the NVT, all the energies are actually fluctuating, the total energy, the potential energy and the kinetic energy. So now it's important to see what this T damp does. So like I told you previously, the T damp value is about I think 100 times the value of the time step. So in this case I gave a slightly lower value of T damp. So if you change that value and if you ran the simulation and you took a look at the temperature profile, somewhat changing it more frequently than what it was for the value of 0.1, right? So essentially this is some parameter that is telling you how quickly you want the system to reach the temperature that you actually are desiring, right? This is actually a parameter with which you have to, if for certain systems you may have to play with, okay, and you will know whether this parameter is actually good or not only when you have tested whether it has reached equilibrium or not. Temperature at least is okay, usually you will be able to reach equilibrium, but pressure, especially for solids, you can have a hard time. Okay, it will you will say 1 atmosphere, but it will take a very very long time to reach that pressure and the fluctuations can be huge. So in that instance there might be a need where you have to tweak these P damp parameter a little bit. The next exercise I just do it for a slightly larger value of 0.5 for the T damp. This is exactly the same simulation except that I have changed T damp to 0.5, but you see that the oscillations are a little bit less frequent, which means you are giving it more time for the system to actually reach the system to the desired temperature. The same behavior is also observed for P damp. Okay, if you have larger values it will look more like that, whereas if you have smaller values it will fluctuate wildly about the temperature that you are requesting, and you will know whether that is right or wrong when you stop it and check for equilibrium.
This is also, so here so you're saying both of this is not desirable. Is that the plan?
No, to bring it to equilibrium you may have to change these things a bit.
So if we need to find one which was like previous first,
Yes.
like exercise 4.
Yes. Again, these are just visual conclusions that we have drawn. So like I mentioned, you will know which of these things is right when you are testing for equilibrium. Otherwise you won't know. Yeah.
Both will bring it to equilibrium, it's just that it will take more time.
This might take more, this will take much more time.
So
Yeah.
if we wanted to get it to equilibrium in shorter time, we should anyway
But yeah, correct, but there can be issues if you are lowering these values to a great extent also. Okay, there is some thing that will break down if you are decreasing it to a ridiculously low value. So you can't do that too much.
What will take more time?
So if you give a larger value of T damp, you saw the temperature how it was equilibrating. It's like this, right? For a value of 0.01 it was like this, and for a value of 0.1 it looked like this. So I am illustrating what this T damp is doing to the temperature. Okay, now what is desirable or what is not desirable you will know only when you are testing the system for equilibrium and seeing if it has reached the temperature that you want. So basically after doing this exercise, after NVT you have to stop it and do an NVE run to check whether the temperatures are oscillating about 300 Kelvin. Now, it may so happen that you have done it so slowly, but you have done it for a fewer time steps that your system is still not reached equilibrium. You are seeing what I am saying? You are understanding what I am saying?
Yeah, it has been done so slowly that still the system hasn't
Reached equilibrium. But the same, for the same time step, I may be able to use a lower value of T damp, which may bring the system to equilibrium in the same, for the same time period.
So T damp is related to how fast heat is being pumped from the bath.
Correct.
So
How fast you want your system to reach the temperature that you desire.
if the value of T damp is low, then heat is being pumped.
Extremely fast. You wanted? It's okay. So then I say perform an additional NVE. So exercise 7. So let's go to exercise. No, exercise 6. What was exercise 6? That's also done. So exercise 6. So in exercise 7, after doing this NVT, I am checking if my system has actually reached equilibrium once again. So that's my temperature profile. So this was my NVT oscillation with T damp equal to 0.5, and then I am stopping it and I am checking if it's oscillating about 300 Kelvin. I am satisfied that it has reached equilibrium at 300 Kelvin. So I think it is at 300 Kelvin. Now the pressure is still way off, will still be way off, it will not be close to 1 atmospheres. So we need to perform additional NPT runs. Now the 300, it was now previously what did we do? NPT from 150 to 300 and then you stopped it, it was not oscillating about 300. Now what we have done, we have exclusively just used NVT to bring only that, make the temperature oscillate about 300. So the system is well thermalized and is going to be at 300 Kelvin. Now I just, if I use the NPT thermostat, I will reach the required . So what I do is after this run, NVT, I check for something. After that I do once again NPT, but this time the temperature is 300 to 300. Point 1 and ISO 1 bar, and I've given a arbitrary PDAM parameter of 0.5. Okay, and then again I check whether the system has actually reached equilibrium. Okay, so I'll just come to it 1 minute. I'm just going to talk about it in a bit. So that's the temperature. Okay, that's the temperature that it has reached. And that's the pressure. Okay, so now this is difficult to read. It looks like it is 0, right? Because we started off at some insanely large value, it looks like it's 0. But if you now look at the log lamps, it's, oh sorry, what exercise were you looking at? Exercise 8, right? .007. So it is reached equilibrium at 1 atmosphere. This is at NVE. This is at oscillating about 1 or so in the NVE ensemble. So the pressure has reached equilibrium. The temperature has also reached equilibrium. So we have our system, the argon gas, at 1 atmosphere and at 300 Kelvin. Now you can go and check if PV is equal to nRT for the system, and it will. So multiply P and V here from the simulation and do nRT there, and you will get your, it will satisfy the ideal gas law.